Welcome to this deep dive. Tailored just for you. We're jumping right into PyTorch today.
Yeah, it's a really powerful tool for machine learning, deep learning, all that good stuff.
Definitely. And you shared some great material, so our mission really is just to unpack that core PyTorch workflow, the fundamental steps.
Exactly. It's like a standard process you follow. The sources you sent, lay it out pretty clearly. You start with data prep.
Getting it ready for the model.
Right. Then you build or maybe just pick a model.
Mm.
Then the big step, fitting it to the data,
Well,
training it.
okay. Making predictions.
Making predictions, seeing how well it did evaluation.
And then trying to make it better, experimenting.
Yeah, tweaking things.
Right.
And finally, you got to save the model, right? So you can use it later without retraining.
Makes sense. And to kind of see all this in action, we're using that classic example. Just learning a straight line.
Perfect starting point. Simple, but it shows everything.
Cool. So let's dive in. That workflow you mentioned, 6 steps. Step 1, data preparation. How does that work?
Well, you've got raw data, maybe spreadsheets, images, could be anything. But models need numbers. So we turn it into numerical representations, tensors in PyTorch.
Tensors, right.
And your sources show this by creating some synthetic data. They actually make data that follows a perfect straight line.
So we know the answer beforehand, like y equals 0.7, x plus 0.3, that formula they use.
Exactly. They use torch.arrange for the x values, plug them into the formula. Boom, you have x and y. It gives the model a clear target.
Okay, so we have our perfect data, but then there's this crucial bit about splitting it. You mentioned that, an 80-20 split.
Yeah, that's super important. Think about it. If you study for a test using the exact same questions that are going to be on the final exam.
You'd ace the test, but you wouldn't actually know if you learned the material properly.
Precisely. So we split, we train the model on one chunk of the training set, maybe 80%.
And hold back the other 20%, the test set.
Right. The model never sees the test set during training. So when we test it later, we get a much better sense of how it'll do on new unseen data generalization.
Gotcha. That makes total sense. Okay, step 2, building the model. Neural networks. They sound complex.
They can be, but the basic idea, they're algorithms that learn patterns from data.
Yeah.
That's kind of it.
And the example uses a linear regression model class. It inherits from nn.module. What's that?
An n.module is like PyTorch's base building block for all neural networks. It provides a lot of the underlying machinery. You build your custom models on top of it.
So our linear model uses this nn.module, and when it starts, its guesses are pretty much random, aren't they? The weight and bias.
Totally random. Well, initialized randomly. Your source mentions starting values like weight 0.33, bias 0.12, something like that, way off the 0.7 and 0.3 we actually want.
And the learning process is about fixing those random guesses.
Exactly. Inside the model, there's a forward method that defines the calculation. How does an input x turn into an output y using the current weight and bias?
So it applies its current, probably wrong understanding of the line.
And we use torch.nn for pre-built layers or components. And crucially, torch.nn a parameter to tell PyTorch, hey, these things weight and bias. These are the parameters I want you to learn.
Okay, data's ready, model's built but clueless. Step 3, fitting the model, training time.
Yep, this is where the magic happens. It's iterative. Trial and error, essentially. The model makes a prediction.
And we need to see how wrong it is, the loss function.
Exactly. You need a way to score the predictions.
Yeah.
Your sources used nn.L1 loss.
L1 loss mean absolute error.
Yeah, basically. It just
Okay.
calculates the average difference between the prediction and the actual target value. Simple, robust.
Okay, so we know how wrong it is. But how do we tell it how to get less wrong?
That's the optimizer's job. Like torch.optim.sgd stochastic gradient descent.
SGD, right. Heard of that one. How does it work with the loss?
So in the training loop, which runs many times called epochs, you do a few things repeatedly. First, the forward pass. Make a prediction.
Got it.
Calculate the loss based on that prediction.
How far off we were.
Then, super important, optimizer.zeroGrad. You have to reset gradients from the last iteration.
Okay, zero the gradients. Why?
Because PyTorch accumulates them otherwise.
Yeah.
Then comes loss.backward. This is backpropagation. It calculates how much each parameter, like weight and bias, contributed to the loss.
Like figuring out which knob to turn.
Kinda, yeah. And which direction. Then finally, optimizer.step. The optimizer uses those calculated gradients to nudge the parameters in the right direction, the direction that should reduce the loss next time.
And you just repeat that whole cycle. Forward, loss, zero grad, backward, step.
Over and over. Your sources showed it running for, what, 200 ABOX?
Yeah.
And you can see the loss value going down, down, down. the model's learning.
Nice. Okay, so after 200 APOCs, our model should be better. Step 4, making predictions and evaluation, using the test set now.
Exactly. Time to see how it does on data it never trained on. Use the trained model, feed it X-test.
And you mentioned torch.inference mode.
Yeah, it's a context manager. It tells PyTorch, hey, we're just predicting now. No need to track gradients or anything fancy. Makes things faster, uses less memory.
Smart. And the sources had plots, right? Showing the initial random line versus the final learned line.
Yeah, those visualizations are great. You can really see the improvement. The line gets much closer to the actual test data points after training.
Cool. And step 5 was improvement, experimenting. So maybe try a different loss or more epochs or tweak SGD.
All of the above.
Mm,
Or even a different model structure, although for a line, it's pretty simple. But yeah, machine learning is very experimental. You try things, see what works.
right. And finally, step 6, saving and loading. Because retraining is the pain.
Definitely. You don't want to lose all that training effort. So you save the learned parameters. The standard way is saving the model's state dict.
The state dictionary. So just the weights and biases it learned.
Primarily, yeah.
Yeah.
It's usually just the learned parameters. You use torch.save, model.stateddict, pet path. Path is just your file name, like mymodel.pth.
Okay. And loading is the reverse. Create a new model instance.
An identical structure to the one you saved.
And then load the save state dictionary into it. Load stadict, torch.load.
You got it. Your sources showed loading it into loaded model. It's like
Man.
pouring the learned knowledge back into an empty brain.
Huh, nice analogy.
Hmm.
And they briefly mentioned a V2 model using n.linear.
Oh, yeah, that's just a slightly more concise way to define the same linear layer using PyTorch's built-in n.linear. Does the same thing, just less code. They trained that one too, got similar results.
Okay, wow. So we've really walked through that whole pipeline. Data prep, build, train, evaluate, improve, save. Even for a simple line, all those pieces are there.
Absolutely. And it's pretty cool to see how it goes from random guesses to actually understanding the pattern in the data just by repeatedly looking at examples and adjusting based on the error.
It really is. What's maybe fascinating thinking about it is how that core process, how it applies when things get way more complicated than a straight line, like images or text or, the kind of complex problems you might be facing.
That's the key question, isn't it? How do these fundamental building blocks scale up? How do you adapt this workflow for your specific data, your specific goals?
Definitely something to chew on. Keep digging into it. And remember, every deep dive like this just gives you a new lens for looking at the world through data.